Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. In this video, I want to talk about three related interesting moduli problems that occurs in mathematics. In the first one, I want to look at the four subspace problem, revisit that, and introduce the concept of semi-stability. This is an algebraic moduli problem that occurs and that uses geometric invariant theory. From then, I will pass on to a geometric moduli problem, and that looks at the moduli of 4 points on a line, which is given by the cross ratio. And finally, I want to finish up by talking about M04 bar, which is the moduli of stable curves of genus 0 with 4 marked points. Okay, so let's start with the first one, which is the four subspace problem. And I just want to remind you that that involves a Dinkin quiver, like this one here, called the D4 Dinkin quiver, where there are 5 vertices, 0 up to 4 here, and the outside ones all point to one central vertex, 0 there. Okay, so we want to consider certain representations of this quiver. The representations I want to have a look at have this form here. Okay, so the dimension vector, it's given by a dimension vector, is 2, 1, 1, 1, 1. So the 2 corresponds to the middle here. You want a two-dimensional vector space K2, and basically you just want 4 linear maps from K to that K2. Okay, so that's the setup that you have, and so basically this is just given by a set of 4 linear maps from K to K2. So basically you just need to give me 4 vectors inside here. Okay, so that's the space you're looking at, the representation space. And remember, this is a geometric invariant theory situation, because there's a group acting on the set of these. Okay, so remember, you can change bases for each of these 5 vector spaces, and that change of basis is GL2 for the middle one, multiplied by 4 copies of GM, 1 for each of the outside vertices. And remember that the diagonal copy of the scalars acts trivially, so we can factor that out and we get PGLD action on the set of all these representations. Now, to do geometric invariant theory, the way Mumford set it up is you should put a stability condition. And King's theory of stability conditions involves picking a vector like this one here, -2, 1, 1, 1, 1. It has to be a vector such that when you take the dot product with this D, you get 0. And in this case, we see we get -2 times 2 is 4, plus the 4 ones does indeed give you 0. Okay, so what does this stability condition do for us? Okay, it means that we should throw out certain representations according to this stability condition. Okay, and they're the unstable ones. So let me show you that if any of the VI equals 0, then that gives you an unstable representation. Okay, so let's suppose that your I here is 1, so V1 is equal to 0. I want to show that that's unstable. So let's remind ourselves what we need to do to show that. We want to find a sub-representation, so I'll show this as a sub-representation, such that its dimension vector, when you dot it with this theta, the stability condition, is positive. Okay, so what's the sub-representation I want to look at of this one here? I want to replace all of these with the subspace 0 and keep this one here. And this map, remember, V1 we assumed was 0, so it restricts to a map from K to 0. So you can restrict the codomain down to 0 and it's still a map. And so that means that this is a sub-representation. And what's the dimension vector of this sub-representation? Well, it's 0 in these 4 slots, in the 0th, 2nd, 3rd, and 4th slot, and it's 1 in the 1st slot. So the dimension vector here is C equals 0, or 1 in that 1 slot, 0 in the 0th, and the other slots here. Okay, and when you take the dot product of this, of course, you just get the 1 times the 1 here, which is strictly positive. And that shows you that if any of these linear maps is 0, then in fact you get an unstable representation. So we'll throw those away. Okay, so if this map is not equal to 0, then since this is one-dimensional, in fact, this is going to be injective. Okay, so we can assume that these 4 maps here are injective. So if they're injective, well, these of course are one-dimensional, so that will define a one-dimensional subspace of K2. So this is how we get the name, the 4 subspace problem. So in this case here, you'll have 4 one-dimensional subspaces of K2 that we're looking at. Okay, so the other thing that you should notice is that, well, if you have a one-dimensional subspace of K2, right, then that corresponds to a point in P1. In fact, we're looking at maps here. So if we scale them by GM, right, we're allowed to scale each of these by GM, of course. That means that essentially the data that's involved once you mod out by this scaling by GM is precisely just the one-dimensional subspace that's the image, okay? So up to this GM action, really, these are just giving you 4 points inside the projective line. And that's the way we'll pass from this algebraic problem to this geometric problem of the moduli of 4 points on the line. Okay, so let's have a look at that. So the first thing to note, what is the setup here for this moduli of 4 points on a line? How do we put it into a geometric invariant theory setup? So the first thing is that to note is that PGL2 acts on P1. So why is that this case? Well, remember GL2 acts on two-dimensional vector space here, okay? It acts on K2. And here you want to look at this only up to scalar when you look at P1 and you throw away the 0. So if you do that, that means that on P1, your GL2 action actually passes to a PGL2 action, okay? Because scalars won't change points on P1, okay? If you scale homogeneous coordinates, you'll get the same point inside P1. So PGL2 acts on P1, and so you can let it act on 4 copies of P1. So 4 copies of P1 just gives you basically a 4 tuple of points in P1. Okay, so that's how you should think of it. Maybe one way to think of it is as follows. So what are the points here? Okay, so here's your P1, and you just pick 4 ordered points: Z1, Z2, Z3, Z4. Okay. And you want to look at this up to the PGL2 action, so you can change coordinates on this P1. Okay, so it turns out that there's a stability condition on this setup, PGL2 acting on 4 copies of P1, which precisely mirrors this theta, so I'll call it theta again, such that this GIT problem, so if you want to work out this representation variety, that's the set of all of these, which is basically just 8-dimensional affine space, since it's 4 copies of 2-dimensional affine space. Okay, you look at the theta semi-stable part of that and you mod out this by this PGLD. That's precisely the same as if you look at the theta semi-stable part of 4 copies of P1 and you mod out by PGL2. Okay, so they're the same moduli, geometric invariant theory problem. Okay, so this one's more geometric, involves points on P1. And this is algebraic, okay? You're looking at representations here and isomorphism classes of representations. Okay, so let's continue and try to analyze this GIT quotient over here, okay, by saying what precisely are the theta semi-stable points on these 4 copies of P1. Okay, so what is that, okay? So we use the semi-stability condition already to show that you do actually get points inside here, okay? So quadruples inside P1, okay? But let's work out precisely what this is, okay? So remember, to do that, what do you do when you have to check semi-stability, okay? So what you need to do is you need to look at sub-representations of this, okay? And you get instability when that sub-representation gives you a dimension vector with positive inner product, dot product with this theta. Now the first thing to notice, in this theta, the only negative term is this -2, okay? So if you have the whole of this K2, then you'll be sufficiently negative, it won't be positive, okay? Because even when you do this theta with the whole thing, you put in as much positivity on the outside from the others as possible, you'll only get theta dot d, which of course is 0, okay? So if this is all of K2, then you'll get something that's stable. If your sub-representation is such that this is 0, okay, if this is actually just 0, then of course you must have all the VI's are equal to 0, and that's unstable. Of course, that doesn't give you 4 points of P1. In fact, none of those are points of P1. So the only other situation where you can get an unstable representation is if the sub-representation is one-dimensional here. Okay, so let's look at the key case. The key case is, suppose our V1, V2, V3, or just the 3 of them, like these 3, they all have the same image. Okay, suppose V1, V2, V3, in other words, define the same point of P1. Okay, so image of V1 equals image of V2 equals image of V3, and that's a one-dimensional subspace of K2, and we'll call that one-dimensional subspace W. Then I want to claim that in this case we get an unstable representation and hence also an unstable point of this 4 copies of P1. Okay, so why is that? What's the representation that you can pick? Well, you're going to replace this with 0. These 3 k's you keep. Okay, and these 3 k's, since the image of them is w, you can make that map into the w here. So you keep these 3 k's. You restrict the v1, v2, v3, the codomain, so it's no longer all of k2, it's just w, which is one-dimensional, and you replace this last copy of k with 0. And that you can see is a sub-representation because we made sure that the image of the v1, v2, v3, okay, which is w, is contained here. Okay, so that's a sub-representation, and let's have a look at what its dimension vector is. Okay, in the 0 slot, it's 1, because w is one-dimensional. In the 1, 2, 3 slot, it's 1. And in the last slot, it's 0. Okay, so that's a sub-representation. And let's take the dot product of this with our theta over here. So you get the minus 2 times the first one, and then you get 3 1s, so you sum up the next 3 terms, 1 plus 1 plus 1, 1 plus 1 plus 1. So here the number of 1s outweighs the minus 2 here to give you plus 1, which is positive. Okay. So in this case, you get an unstable representation and hence also an unstable point of this 4 copies of P1. Of course, you might ask, well, let's try to change it. Okay, so if you just had 2 of them and you replace this with a 0 here, then the only other change is that, well, you change this. This is no longer one-dimensional, so you don't have a 1 here, you have 0. So you get 1 less 1 here, and then it's equal to 0. So since it's equal to 0, in that case, it's still semi-stable. Okay, so you still get a semi-stable point there. So if you have 2 of them to find the same point, that's okay. But once 3 of them to find the same point, that's not okay. And of course, if a 4th one also finds the same point, if you have an extra 1 here, then it's even more positive. You'll get a 4th one here. Okay. So the conclusion to this is we've actually completely worked out what all the theta semi-stable points are for this 4 copies of P1. They're precisely those quadruples, okay, so this is 4 points on P1, those quadruple points where no 3 of them coincide. Okay, and hopefully you know that the moduli 4 points is the cross ratio, and that's what I'm going to talk about next. So let's look at the answer to our GRT quotient problem. Okay, so if we look at 4 copies of P1, P1 to the 4, and we take the GRT quotient of that by PGL2 using the semi-stability condition, the stability condition theta that I outlined there, I get P1. And that isomorphism is actually given by the cross ratio. So let's remind ourselves how that works. Okay, so firstly, P1, we can identify that as a copy of the affine line plus a point at infinity. Okay, so for simplicity, we'll just work with a familiar case where the field is C. Okay, so it's just C union infinity. Once we work in this language, of course, we need to rewrite, well, how does the PGL2 actually work on this here, okay? Suppose you have A, B, C, D, that's your element of PGL2. How does it act on this complex number, which can also be infinity? Well, it acts by this linear fractional transformation. It sends Z to AZ plus B divided by CZ plus D. Okay, you might note that this is only defined up to a scalar. So if you scale this by some fixed non-zero complex number, of course the numerator gets scaled by that amount, and so does the denominator, so this number stays fixed. Okay, you're allowed to put infinity in here and you calculate this the usual way you would expect. Okay, so the point is that suppose you have a point inside here. Okay, so we'll lift it up to a quadruple of points inside P1, Z1, Z2, Z3, Z4, so these are now complex numbers or infinity. Okay, and I want to send it to P1, so that's essentially a complex number or infinity. And what is that complex number or infinity? Well, I look at this, what's called the cross ratio expression here. Okay, it's also a quotient of ratios. Okay, so you can look at this ratio of this on that divided by this on that, or it's just Z1 minus Z2 times Z3 minus Z4 in the numerator divided by in the denominator Z1 minus Z4 times Z2 minus Z3. Okay, so that's the cross ratio. So it's very well known that this cross ratio is invariant with respect to the action of PGL2. Okay, so if you let PGL2 act on this, so you apply this linear fractional transformation to each of Z1, Z2, Z3, Z4. Remember, PGL2 acts diagonally on this. If you let it act on all of those, then this expression doesn't change. And in fact, it's going to give you an isomorphism of these two. Okay. The second point to note, and this is a rather more subtle point, is that we brought in this semi-stability. Okay, so how does the stability come in? Well, look at this expression. Okay, when does it make sense? Okay, so suppose Z1 equals Z2 equals Z3. Okay, suppose 3 of the Zi's coincide. Then you have Z1 minus Z2, these two coincide, so you get a 0 here. Z2 equals Z3, so you get 0, so you get a 0 on 0. Okay, of course that's not defined, okay, so you can't work out what that is. So it's not defined there. But fortunately, semi-stability says that we don't look at those quadruples where 3 of those Zi's coincide. Now let's suppose just 2 of them coincide, okay, that's the semi-stable case. Okay, so these two might coincide, for example, then you get 0 in the numerator. But since these others don't coincide, then we can assume that this is well defined. So it's just 0 on something, so it's 0. Alternately, you could have 0 in the denominator, but if these are non-zero, then you can define that to be infinity, and that's that corresponding infinity point in P1. Okay, so as long as no 3 Zi's coincide, this cross ratio is well defined, and this semi-stability sort of tells you exactly what is happening. The other thing to note is that, remember, when we look at this does not precisely correspond to PGL2 orbits inside here, okay? And that's because there are some orbits which might not be closed. And in fact, this does happen. And it happens for the following orbits, okay? So suppose now we're on the edge where you'll have instability if 3 of the Zi's coincide, but suppose the first 2 coincide, but these others are different. So this will give you a sub-representation similar to the destabilizing sub-representation when 3 of them are the same. And that will be the case where this theta dot, that dimension vector C will be 0. Okay? And in that case, we get something that's semi-stable but not stable. And that is when this type of phenomenon of non-closed orbits occurs. Okay? So let's look in here. Now, one of the things that you should know is that if you apply PGL to this, you can send any 3 points on P1 to any other 3 points. So in particular, we can make this Z3 go to as close as we like to Z4, but not equal Z4. Okay, so the PGL2 orbit of these things, okay, you get lots of them. They'll all kind of look like this. You can get Z3 as close as you like to Z4, but it won't equal. Of course, when you take the limit, the closure of that orbit, you'll get it so that you can actually have Z3 equal to Z4. Okay. So in the closure of this one here, you'll have this one here. So these 2 orbits will actually get compressed into 1 point inside this moduli space of 4 points on P1. Okay, so in that P1, okay, there are 2 orbits which get collapsed into 1. Okay, so how often does that occur? Okay, that occurs whenever you have 2 of them coincide. Okay, and when 2 of them coincide, well, you get the same point if you make, so like for example, Z1 equals Z2. Okay, you might as well coincide the other two as well. Okay, that will give you the same point of P1. So basically, you want to say, how can you break up the 4 points into 2 pairs of 2? Okay, so basically, you want to choose 2 of them out of 4. So that's 4 choose 2, which is 4 3 so 12 divided by 2 is 6. And then, of course, since it didn't matter whether you choose Z1 and Z2 or Z3 and Z4, you divide that by 2. So let me just divide this by 2 for you. So you really should put a half here. You get 3. So there are 3 special points of P1. Okay. So that's how the cross ratio gives you this moduli space of 4 points on P1 up to the change of coordinates on this P1, so up to the PGL2 action, and you have to realize that you have to include this stability condition theta here. Okay, so this is well defined. Okay, now I want to talk about a very, very important moduli problem that occurs in algebraic geometry and in physics. That's the moduli of stable curves. Okay, so I want to look at the simplest interesting one, which is related to this problem, which is M04 bar. Okay, so this is the moduli of stable genus 0 curves with 4 marked points. Okay, so essentially, I don't want to get into the details of this. Genus 0 essentially means you want rational, so it's like P1. Okay, stable means that you want to make sure that on each component, rational component of each P1, you have at least 3 special points so that there are no automorphisms of that P1. And the key difference between what happens in this case here and what we were looking at before is now we're going to actually allow the P1 to vary as well. So it's not just the 4 points that can move around, okay? You're going to allow the P1 to vary. So let's just see what I mean by that, okay? So suppose you look at this conic inside the projective plane in XYZ space, Z plane, okay? So lambda here is non-zero, and this will give you a smooth conic. And being a smooth conic means that it's isomorphic to P1. It's a copy of P1 embedded inside P2. Okay. Now, of course, we can vary this conic inside P2. How? By, for example, taking lambda going to 0. And as you let lambda go to 0, this degenerates to x squared minus y squared equals 0. And of course, in that case here, this factors as x minus y equals 0. That's one line. Times x plus y equals 0. That's the other line. So this P1 can actually degenerate into 2 lines. Okay. But otherwise, we're going to have essentially the same problem. Okay. So it's going to be 4 points on this stable genus 0 curve. Okay, so this M04 bar, it's going to turn out you're going to get exactly the same moduli coming out of it. At least the coarse moduli coming out of it. That's P1. But it's quite a different problem, and I want to show you how you can represent it and see what's going on. So the situation looks slightly different there, and it's rather interesting. Okay? And also show you a different way to view this GIT problem. So suppose you look at a fairly generic sort of case where Z1, Z2, and Z3 are distinct, okay? 3 distinct points on P1. Then you can use PGL2, of course, to send those 3 points to any 3 points you like. So let's suppose we fix them to 0, 1, and 3. So here's a P1, for example. You have Z1 equals 0, Z2 equals 1, and Z3 equals infinity. Okay? And the Z4, you're going to let roam how you like. What I'm going to do is I'm going to draw the universal family U. Okay? So what's that going to be? Okay? So what do I mean by universal family? So the moduli here is going to be P1. So here's my P1. And what does it mean to be a moduli? It means that for each point of this P1, I'm going to give you a stable genus 0 curve with 4 marked points. Okay? So here the curves I'm going to give with the black lines, and the markings I'll give with the blue. Okay? Markings are with blue. Okay? So let's just pick one example. Okay? So we'll take one point on this moduli space on my P1, which is M04 bar, lambda. Okay? So this is going to be the universal family. So I'm going to look above that. I'm going to draw this line, this black line. That's a P1. Okay? And now, this is a copy of P1, so it's a genus 0 curve. And it has 4 marked points on it given by the blue, where it intersects the blue. It'll be Z1 equals 0, Z2 equals 1, Z3 equals infinity, and Z4 equals this one here, and that's going to be lambda. That's going to be given by lambda. So I'll write that in blue. Lambda here. Okay? So there's your lambda. So that's one example here. And what you do to be a universal family means that, well, as you move this lambda along this P1, you'll get a different curve, or maybe the same P1, a different curve, with a different set of markings. And as you do that across, of course, you get a family, a one-dimensional family of curves, of course, you get a surface. And on that surface, you also want to have, for each fiber, mapping down to here, okay, so for each curve, one-dimensional curve, you want 4 marked points. Now, it looks like here I've drawn a P1 cross P1, but actually, for this universal formula, I'm going to have to do something a little bit more interesting, okay? So what I have to do is I have to perform, okay, so if you note, this Z4 is basically, so to speak, the diagonal, so like the x equals y. Okay, it's a diagonal. And it will coincide with this Z1 equals 0, Z2 equals 1, and Z3 equals infinity at these 3 points. Okay, so there they correspond to this situation here where you have double points. Okay, and what we're going to do is, well, this is a surface. This is essentially, so far, it's P1. And being an algebraic surface, we can apply a procedure known as blowing up. So we can blow up this point, and this point. And what that does is it replaces each of these points with a set of tangent directions through it. And since the set of tangent directions through it is a P1, it replaces each of these points with 3 P1s. So it's going to be P1 cross P1 with 3 points blown up. Okay, and let's see what happens, for example, if we look above this lambda equals 0. Okay, lambda equals 0. So that would have been the case where Z1 and Z4 coincided. Okay, so let's look above lambda equals 0. So let's do that, lambda equals 0, and see what happens. Okay, so the curve, okay, so you have this curve here, but you've also blown up. So above this point, you've also got an extra P1. Okay, so this is the curve here. This one here is the pre-image of this curve here, or the strict pre-image, what you call. Okay, but there's an extra what's called exceptional curve, which is the blow-up. Okay, so where are the marked points? Well, blowing up doesn't affect anything outside of these points. It's an isomorphism away from those points. So you still have Z2 equals 1 as a marked point. And Z3 equals infinity. Now what happened to these marked points that correspond to the blue lines through here? Well, let's look at Z1 equals 0 first. Well, it goes through here, so it must correspond to a point on this exceptional. Okay, so which point is it? Is it this one here? Well, what is this point here represented by? So remember, the points on the exceptional correspond to tangent directions. And the one corresponding to this point here is the tangent direction in this direction here. Okay, so of course, this Z1 equals 0 is not in that direction, so it's a different point. So that's Z1 equals 0, so to speak. Okay. And what about this one here? This is also a tangent direction through this point. Okay, so you get Z4 is on the exceptional, and it's also not in this direction. Okay, so it's going to be a different point from both this one here and this one here. So you get a different one here, Z4, and some other point. So we get, rather interestingly, what happens. So these special points of P1, which corresponds to these non-closed orbits here, they look very different in this setup. Okay, so the corresponding stable genus 0 curve with 4 marked points is quite different, because the P1 that you had before, which is what you see generically here, has now degenerated into 2 copies of P1. Okay, 2 copies of P1. Okay, and the 4 points are 4 actual distinct points still. Okay, Z1, Z3 live on one component, Z1, Z4 live on another component here. Okay, so one of the things that you should check, of course, is that this is stable, and to be stable means that on each of these 2 components you must have 3 special points, because if you fix those 3 special points, there are no more automorphisms of that P1 other than the trivial automorphism. Okay, so here you have 3 special points. Okay, because this is a singularity. Okay, so this one is a special point, this one is a special point, this is a special point. So there are 3 special points there. So this bit is stable, and this bit here also has 1, 2, 3 special points. So this is stable. And of course, I hope you can see what the other 2 fibers look like above 1 and infinity. It's sort of similar. Okay, here you've made Z4 combined with Z1. You've paired up Z4 with Z1, and then Z2 and Z3 can pair up. You could also combine Z4 with Z1, and then Z2 and Z3 match up, or you can combine Z4 and Z3 and Z1 and Z2 match up. Okay, so there are the things that can happen, and they reflect the situation that you have over here. And that's how we have a very interesting moduli problem. It's actually a different moduli problem, as you can see from the individual members of the family here, but very related to just 4 points on a curve. And this type of example is extremely important in algebraic geometry. It's still the subject of much research at the moment, and occurs very much in physics. I hope you enjoyed this adventure in pure mathematics.